Okay, so thank you for the introduction. My name, as already being said, is Micha Hallburger, and I'm happy to present our paper, I Still Know It's You, on challenges in anonymizing source code, a joint work with Erwin Quiring, Roland Meyer, and Konrad Rieck. So, as we are talking about anonymization of source code, why should we even care about this? Isn't it just enough to not put our name onto the code? If you think about how you write code and how others write code, even for the same task, most likely the code wouldn't look the same. So every one of us has tendencies to use different data types, to use a different layout, or to nest the code more than others. So we have all this little difference in our code, which sum up to some unique coding style for every developer. And in the last years, there were multiple research papers about how to use machine learning to capture all these little differences and use them to then identify the author of the code, even if the name isn't there in any case. So we have this kind of authorship attribution methods which are able to identify the correct author out of hundreds of possible authors, and they provide a good accuracy of sometimes about over 90% from state-of-the-art methods. So we don't need the name somewhere in it to know who the author of the code is. And as this is some problem for our privacy, there also came some research papers with the idea of using adversary examples to induce misclassifications into this classifier. So they try to use the code and modify the code to disturb the coding style or imitate the coding style of another developer until the classifier wouldn't predict the correct author anymore, but any other developer. So at this point, we could ask, well, haven't we solved this problem? And if we look a little bit closer, it's a bit more complicated because we don't only have the prediction of a classifier, but we also have confidences for all of the classes. And if we look at this misclassifications we induce with such of the evasion methods, we often see a picture like here on the right-hand side, where now some wrong developer has the highest confidence, but the true developer is still at the second place with also some very high confidence, and then there's a large gap until the next author comes in. So this evasion techniques only change the top author, and in the confidences we have still some clues about what's going on, and so the author is still at the risk of being identified. So that's not what we want if we want to talk about anonymity. So what we would want to have is something like this, where the coding style is indistinguishable now, and the classifier isn't able to differentiate between some authors, so that we have for multiple authors the exactly same confidence. And if the classifier would try to predict the author, it just isn't any reliable prediction there. So, and to put it in a more formal way, we defined anonymity for source code based on the concept of k-anonymity we know from data anonymity, and we defined it as given an attribution method, our source code or program is k-anonymous if the confidence of the true author is identical to at least k-1 other authors, so that we have an anonymity set of k authors with identical confidences, and the classifier wouldn't be able to make any prediction. But here's a small catch at the beginning of the definition. We need to know the attribution methods beforehand. But in practice, usually we don't know what attribution method an attacker would use. We might not only know who the attacker could be. So for practice, we would need something we call universal k-anonymity for source code, which is just the k-anonymity, but now for any possible attribution method, and not just a given one, so that we can be sure that we are anonymous against every possible attacker, and that we can guarantee some kind of anonymity here. But unfortunately, as we have proved in our paper, this is incomputable, so we can't get there. And as we can't get there, our idea was now, maybe we can at least measure how far we get. And therefore, we introduced the concept of k-uncertainty, which is kind of the same as the k-anonymity, but now we don't enforce the confidences to be exactly the same, but we allow some room in between them. so that we have a range of the k nearest authors, the k nearest confidences, which are in a range we defined beforehand for some constant, and then this range has to be lower than this constant. This inherits also the problems from the k-anonymity, but we can twist this concept a little bit around to make a numerical measure out of it, so that we now can measure how close we get to the k-anonymity by just subtracting this range, this maximum confidence minus the minimum confidence inside of this k nearest confidences, and subtract them from 1. And then we have a measurement which it would be 1 if we are k anonymous and 0 if the author is perfectly identifiable. And with this we have a tool to at least evaluate how far we get with current methods. And that's what we then done in our evaluation. We took 4 different candidate techniques we thought about could probably disturb the coding style or change the coding style. And we used some kind of code normalization, which should implement something like the code style guides we know from open source projects or from companies. We try to imitate some coding style, which is one of the evasion techniques, which want to introduce some misclassifications. And we also try to obfuscate the code. The code afterwards is not readable anymore, but as a upper bound how far we could get by preserving the semantics of the program and don't care about anything else, we thought it might be a good idea to see how far we can go. And we tested this in 2 scenarios. One where the attacker is aware of the protection and can adapt to it, and one where the attacker is not aware of the protection. And we now want to look at the adaptive scenario where the attacker is aware of the protection, so that we can have some countermeasures against this protection things. And for our evaluation, we did some kind of adversarial training, so we know what the protection could be. Then we tried to protect our training data and then train our classifier again. And as you can see here in the plot, most of these candidate techniques, if the attacker is aware of the protection, are more or less equal to the case where we have no protection. So there are little differences, but they are not that big. The only thing which stood out here is a strong obfuscation, which has a pretty high score in our k-uncertainty. But even this doesn't reach the good protection which we defined in this experiment at 0.99. So even with very strong obfuscation, we are not able to anonymize our code if the attacker knows that the code might be anonymized. So to sum all of this up, defending against code stylometry is complicated and very hard. This universal anonymization is incomputable, so we can't get all the way. And even with what we have currently on methods, with a strong obfuscation, for example, this might be suitable in some way, but it's not readable anymore, so it wouldn't be useless. It would be useless in kind of every program, any project we would do. So even if this would provide some suitable protection, we can't use it in practice. So we need some novel ideas here how we could tackle this problem, because as we all know, the capabilities of machine learning are rising and rising, and also this kind of authorship attribution methods are getting better and better, and we don't have anything to protect against them now, so how could we protect against them if they got any better? So we need some new concepts here to somehow protect developers against this kind of authorship attribution. So that being said, thank you for your attention. Our code from our evaluation is available on GitHub, and I'm open for questions.
Hi, so if I'm correct, doesn't your group have an anonymization method that you used using Monte Carlo rollout simulations, and why did you not evaluate that method in this context?
this is exactly the method we used in our evaluation. This is the imitation method. So this was a paper from Erwin Quiring, which he also published and the code for, and it was called Code Imitator. Therefore, we used it here as we had the code.
So that's not a manual imitation. That's a
No,
using
all of the things are automated.
Okay. All right. Thank you.
Hi, thank you so much for the talk. I just had a provocative question. You showed, you said there's need for more research into this, or another option is that it's simply impossible to anonymize code. Just as it's simply impossible to anonymize your, the postcards you're sending to your parents or grandparents from your vacation because it's personal after all. If you anonymize it, you change the meaning. If you if you anonymize it, you change the meaning, and some things will not work anymore. So, can you comment on that? Do you think there is potential to do better, or do you just think it's a lost battle?
Yes, that's a tricky question. So there might be ways to get at least better than now. For example, where we have already new code language. We tried this on C, but there are new code language every year. So maybe we need some language where we don't have this much of possibilities to write the same code in different ways, so that we can, for example, at that stage, also prevent some kind of coding style. And also with some kind of generative AI, like large language models, maybe there is a chance to at least get closer to this. But we will have to see for new methods there.
We could take one more question. Thank you for your talk. I had a question about scalability of the methods. You mentioned that it's fairly hard to obfuscate or anonymize source code, but it seems that you only study like 30, 80 people, or like at least people coding. And I wonder how you think this would scale to something like GitHub or GitLab with millions of people. Surely it's much easier to get obfuscated amongst millions on GitHub than in, say, 80 people.
Yeah, so in our experiments, we had only 81 people in the large experiment, but as for the attribution methods, they scale pretty well. So they have some evaluations with, for example, 1,600 developers, and they are able also there to achieve an accuracy of over 90%. But of course, if we look, for example, at GitHub projects where we have most of the time not only one developer for a single source code, for a single file or a single project, but multiple authors, and we only have these fragments, it gets more complicated, of course. So, but the authorship attribution methods are on a way to get better at these things, but they are not there at the moment. So we have, for this fragment thing, to wait how it would go. For the obfuscation of whole files, with more developers, of course, it gets harder, but from what we have seen in our evaluations, I won't think that we will get really near to K-anonymity. We get maybe closer, but I don't think we will reach it.